Hello, I'm Doug, stand-up physicist. Remember that movie Good Will Hunting? A math professor at MIT writes a problem on a blackboard, and a secret nerd elf goes and writes the answer. The elf is a troubled janitor, lots of emotional traumas. The janitor finally comes to terms with his nerdliness, and he goes for the chick in the end. That's Hollywood, written by Matt Damon and Ben Affleck, with Robin Williams and Minnie Driver. Here's the scientific reductionism. Nerds need to know. Answer is written on the blackboard. Nerds recognize it. And it has a happy Hollywood ending. I am a continuing ed student and researcher in theoretical physics, who comes from an experimentalist background. So I decided to do the Good Will Hunting experiment at Harvard University. What do they want to know at Harvard? I mean, shouldn't they know everything? Well, I would try and write the answer on the blackboard and see if it would have a happy ending. Professor Christopher Stubbs is the chairman of the physics department at Harvard University. And he gave a talk entitled Confronting the Dark Energy Crisis in Fundamental Physics. Now, the title is a public admission that physics nerds have a profound need to know something. The lecture was packed because that guy was a very entertaining speaker. He had great experimental data, and yet we've got lots of problems surrounding mass. I mean, gravity basically fails for the Big Bang. It fails for the rotation profile of galaxies, and it fails for the accelerating universe. We have hypotheses for all three of these. That would be inflation for the Big Bang, dark matter for the rotation profile of galaxies, and dark energy for the acceleration. And yet all of those have huge problems. The mass of these three is not like any other kind of mass out there. And this stuff gets a lot of stuff done. And yet we don't have the slightest idea of what would be even a reasonable hypothesis for these things to really be. And yet they all have problems with one law, and that would be our law for how gravity works. And I just want to make sure you understand, inflation is not dark matter, is not dark energy. These are three separate hypotheses to correct three different problems with how gravity is used to explain how stuff in the universe moves around. He said the current situation is like this. We've got all the data for the photoelectric effect, but no theory whatsoever to explain it. None. This is a serious problem. Now, they do have good theory people at Harvard University, but he said they've got the exact opposite problem. They have all theory and no connection to data. So the nerds at Harvard, and basically every other university, it really isn't Harvard exclusive here, needs a new approach to how mass and gravity work. Something that is so specific that it could be tested. So my thought was maybe I could write something on the blackboard that would meet those qualifications. My boss let me out of work early, and before the lecture they served tea. Oh yes, that sounds so Harvard, don't you know? On the fourth floor of the Jefferson Labs. You get to mingle with your physics friends and have some tea and cookies. Sounds really good, except I don't have any physics friends. And I'm a diabetic who has to avoid gluten, so I can't eat the cookies. And I think I've got this unified field theory, but I'm not very good at physics. And I just really feel like a total jerk. I really eat away at myself in these kinds of things. Not knowing anybody, thinking I might have the right answer, and yet knowing it's not an easy thing to explain. So after 5 minutes of self-torture, I skipped the T to look for a blackboard. And at one end of the 4th floor is the lab, the library, sorry. And at the other end is the string theory sanctuary. And I call it that because they have really nice blackboards, really comfy chairs, an expensive espresso machine. And it really wasn't the right place for me to just like barge in and start writing on their boards. But between the two is a gorgeous floor-to-ceiling chalkboard. And I mean, this thing was professionally clean. There was like no chalk dust there. There was, however, chalk. So, I mean, I thought maybe people use it. And since it was so clean, nobody would mind if I wrote on it, right? So it took about a half an hour to write this up on the board. There are 11 steps in all. And I really enjoyed this part of my visit. I mean, because I got lost in the groove of math. Now, maybe you haven't done that. Maybe you do gardening, or painting, or a crossword puzzle, or something like that, where you get in this groove and you're quiet and your mind's like working and it's putting everything in its place. And when something isn't quite in its place, I mean, you spot it and you feel good about spotting it, and you keep on going like that. And that's what it was like to write these 11 points up on the blackboard. And so I went back to the T and sat down by myself and realized, oh, I forgot to write my email address there. Because unlike the film, I don't hang around Jefferson's labs every day for somebody to discover me. So I wrote my name. I took some photographs kind of in a hurry because I was starting to feel like a jerk again. And, I did my thing. So let's take a good look at this blackboard. The people walking down this hall would be very smart and very, very busy. So what if they did a really quick assessment of what was written there? And to do that, just like speed reading, you read the title, the first sentence, the last sentence, and see how it goes. And so the title is A Testable Unified Field Theory. Well, that would certainly be very important. And you start with the Maxwell field equations. Well, that's true, and that's a very reasonable place to start. And then the final one was a metric. The metric differs from general relativity for light bending around the sun, 0.8 micro arc seconds more bending. You can't get much more specific than that. So just a speed reading exercise says this might be worth reading the stuff in between. Okay, so I always number my steps, and the reason is that it forces me to define my point of departure. So step 1 is that we start with the best, Maxwell, the Maxwell equations. He is the tallest giant in all of field theory, not Einstein, not his field theory for gravity. Because this treatise was written in 1865. And what's amazing is that the field equations were not modified by special relativity. In fact, special relativity looked to the Maxwell field equations and said, hey, we've got to invent ourselves. Or that's what Einstein did, because the speed of light is constant for everybody. And so it was actually looking deeper into the Maxwell field equations that special relativity was born. And another huge invention was quantum mechanics. And the field equations were not modified at all. The interpretations were changed. What were classical potentials became operators, and the meaning of gauge freedom became much deeper and all that sort of things. But two 20th century tidal waves in physics really didn't move Maxwell. That's pretty amazing. Then there's what I call look and see physics. If you can see a symmetry, then there is a conserved charge. The action is symmetric in time. There's like no t. So this equation is going to conserve energy. The action is symmetric in space, no x. And therefore it's going to conserve angular momentum. The action is symmetric under rotation. There's like no angles in there. And therefore it's going to conserve angular momentum. And the action is symmetric under gauge transformation. Okay, that's a lot harder to see. It has to do with that minus sign that's in the field strength tensor. But that's why electric charge is conserved. And the action is symmetric under change in metric, and therefore mass is conserved. Now you do have to supply the metric as part of the background of the theory, and that's why you need general relativity. But it still is consistent with mass being conserved. So if you can spot all of these symmetries and understand their meaning, you have a darn good physics education. I mean, a great physics education starts with a profound appreciation for the Maxwell equations. And anyone wise will tell you that sort of thing. In step 2, we do an upgrade to the tensors used in the action. Now, tensors can add, subtract, and be multiplied by a scalar. The challenge is to improve tensors without breaking them in any way, because that'll be very bad. So I can actually include multiplication and division so long as I work in 3 dimensions for space and 1 for time, space-time. Now that's a good constraint because that is the way the universe is. It is made out of these 4 dimensions, 3 spatial and 1 in time. Now you cannot in general multiply and divide tensors. It makes absolutely no sense to talk about that in 10D or 11D. And the thing is that the people on the 4th floor here, they work in string theory, which works in 10 or 11D. Now, just it's step 2. If my constraint that you must be able to multiply and divide all your tools, that means that string theory is not a valid hypothesis, not a valid framework to do anything. So it's kind of like a direct threat by the time I get to step 2, so maybe nobody on this particular floor will like my work. But they should get the math. I mean, it basically, it's the mathematics of quaternions, and even if they don't work with those, they certainly work with vectors, and it's basically the math of vectors kind of stripped down and just formalized in just a couple ways. So cats this smart will be able to get, this product here, minus E plus B, and then if you change the order, the B will flip sign because it involves a curl. And they should be able to get the contraction that you get this B squared minus E squared, and that's actually the very kernel of the Maxwell action. They should know that. So in some ways, step 2 is dead dull. I mean, it's only a rewrite. And yet, we do get one interesting thing out of that. We get the pointing vector for free. And when something shows up for free, it tells you that your math is pretty darn good because a math accident that means something indicates you're working with a really nice structure. In steps 3 through 5, I basically plug in new symmetries, and therefore we're going to see new conserved quantities. And I can do this because I now have a division algebra, and so I can just substitute different sorts of things. I can upgrade to the SU2 symmetry, which is also known as unitary quaternions. So since I've got quaternions all over the place, why not put in a unitary quaternion? And that's actually related to the weak force of beta decay. And one way to write this is as a quaternion exponential. So you basically plug in SU2 there, and the action necessarily has that symmetry. In step 4, I upgrade to electroweak symmetry, and that is U1 symmetry times SU2. Now U1 is what's known as abelian, which you can multiply it on the left or the right. And you say, but quaternions don't have that property. And that's true in general. However, you can commute with yourself, which is what happens in this expression. So I call this cute trick number 1. And in step 5, we reach out to the strong force is simply by using 2 of these together. Oh, but there's a little trick in here. And the problem is that if you just multiply 2 of these together, well, this is group theory, so you just get another element of exactly the same group. So I have to put in a conjugate operator, and then it will have a different multiplication table, and this thing clearly has a norm of 1, and it clearly involves 8 little generators, and so it certainly sounds like SU3, and so I call that cute trick number 2. So people have been looking for even larger symmetries, things like SU5 and SU10, and somebody's even working with E8, the monster group, which is as big as the finite guys get. And this is actually smaller. It's got only 8 generators. And some of those quick folks who might watch this will say, no, that can't be right. We know we've got all these particles. And it's like, have you talked to an experimentalist? You can't isolate a quark. You can see photons, you can see W's, and you can see the Z, but you can't isolate these things by themselves, and that's actually due to this thing called confinement. But why is there confinement? It'd be nice if there was a math reason, and I think it may be, because we have one potential with photons, W's and Z's, that's the electroweak sort of thing, and you have this other one in order to make it go. And if you only have one of those 4, you can't get the strong symmetry. You really are required to have 2 sets. And this is not really this is a hand-wavy kind of argument that you'd call it. But at least it sounds like it's got some kind of reason behind it. You really need 2 sets of W's, Z's, and photons before you start to get into the kind of gluon area. So any serious physicist, though, is not going to take the preceding argument too seriously. And that is because too much work really needs to be done by credible people to be anywhere in the neighborhood of acceptability. I mean, I've seen the complex thoughts of people who do actual field theory, and this is just not enough for them because in a lot of ways it moves in the wrong direction. It moves in the direction of simplicity. Too bad for me and nature. Because she somehow has the ability to do this every time with the simplest damn things possible, and so I think we got to move that direction. But selling it is going to be, as I say, I don't know how it's going to happen. All right, so we can see all these symmetries in step 5. The symmetry for EM, for the weak force, and the strong force. And so now all we have to do is get out to gravity. Not so fast. Because this is going to be a little tricky. This has got to involve a trick somehow. Because we're going to assume the same things as general relativity. And that is that there is this connection that is metric compatible and torsion free. And what that means is that if you take a covariant derivative in curved spacetime, the derivative has 2 parts. One part is for changes in the potential, and the second is for changes in the metric. The metric is symmetric, So changes in the symmetric metric will also be symmetric. But if I am looking for symmetric changes with quaternions, I'm not going to be able to track them, because the curl that shows up when you start doing that sort of thing, that's anti-symmetric. I don't have a way to keep track of these things. I can't do it with quaternions. I need a tool that is more symmetric than quaternions. So in step 6, I start doing things with upgrading from quaternions to hyper-complex numbers. There, everything is positive. And I've written up my 4x4 matrix representation. I make sure there's always an inverse, and you can do that by excluding 0 and all the eigenvalues for this matrix representation. And that's actually cute trick 3. It's really actually kind of cool, because eigenvalues play this central role in quantum mechanics. And I'm trying to drive out to gravity, and I say, yeah, and I can't use any eigenvalues. It's the way the math works. You know, we got to accept it, I hope. Now in step 7, I apply the Euler-Lagrange equations. That is the absolutely standard way to generate the field equations. This is a thing you just plug in and you grind it out. And you actually see a form of Newton's law that's consistent with special relativity. In step 8, I show a static solution to those field equations if the potential is constant. In that case, it's got to be all due to the metric, and this metric has these exponentials along the diagonal and nothing else, because of this was very simple symmetric problem I was solving. And that metric is known as the Rosen metric, and it has passed the first order weak gravity field tests. And so that's absolutely huge. It's a starting bar. You got to do that sort of thing. In step 10, I point out that the quadrupole is the lowest mode of emission for gravity waves. So it's going to be consistent with binary pulsar data. Now, why is that? Well, usually what people do is they say, well, here's GR, and I think I'll add something to it. And it's as soon as they do that, they lose this test, because that thing they added is a place where you can store energy and momentum, and therefore if you have an isolated mass, you can actually have dipole gravity wave emissions. That's not consistent with the data. But what I did was I didn't add anything. It's just a symmetry that you should be able to spot in the action itself, and it's symmetric, so I'm going to be able to account for the changes. And it's the simplicity of the theory which allows it to have the lowest mode of emission be a quadrupole instead of a dipole. All right, but step 11 points out that it differs for general relativity by having more light bending around the sun. Now, it's not much more light bending. It's beyond our ability to test right now. Einstein's theory was tested to the arc-second level, and I have to go a millionfold more than that. We've actually done 10,000-fold. We have to improve it by a factor of 100. And then this proposal predicts like 10-12% more light bending. And at that point, other things like the fact that the sun spins and kind of get in the way of the proposal, but hey, that's the way it goes. So that's my answer to the question raised in the lecture. These are new equations that govern gravity, and they can be tested. Yet the Goodwill Hunting experiment at Harvard University was a complete and utter failure. No one replied to anything I wrote. It was not a particularly well done experiment, because I did not monitor this chalkboard. It may have been erased a mere hour after I wrote it up by the professional cleaning crew that really did a great job of keeping that board clean. I don't know. I don't know how many people walked by it while it was up. Maybe nobody hangs out in this place. They're too busy getting to the library or getting back to their office. There are lots of reasons for failure. Failure is not interesting. And yet I don't feel bad about that sort of thing. Failure gives me something to think about. How can I do this experiment better? Now this YouTube video is a variation on the experiment. People can see this over time. The title might just attract people who are into the math physics kind of world, and maybe they aren't pros themselves, but they might know of somebody and say, hey, why didn't you watch this? This was kind of fun. Could you tell me like where it's wrong? And if they come back and say, well, I wouldn't have done that, that's not a good enough answer. You really have to look at the action, and you have to say why we shouldn't just go ahead and do this experiment to just find out whether general relativity is right to second order ppn accuracy. Now, I may send a letter to the professor who gave the talk, Professor Stubbs. Odds are that he's just too busy. But it's worth, one of these postage stamps that's got the Simpsons on it. And I'm just not sure whether I should have Bart or Lisa. I actually think I'll probably do both of them. Because that's kind of, I feel like in between the two, this is definitely obnoxious, me working in my basement here and getting exactly what Einstein tried to do for 30 years. And yet it's really smart. I mean, it's standard, people. I mean, I didn't invent hyper-complex math. I didn't invent Euler-Lagrange. I didn't invent solutions to field equations you get by Euler-Lagrange. That is all standard stuff, okay? An unusual cocktail, but at least it's testable. I mean, that's my biggest frustration, okay? I figure if I say that once to people who work with gravity, it's their responsibility to go and say, well, this part doesn't work. Now, since it's a unified field theory, lots of parts aren't going to be completed by me. There are limitations to what I can do. But, that's my own issue. But let's get back to the film, Good Will Hunting. Because my favorite part was that blackboard scene. I saw the film when it came out, and the blackboard kind of didn't stay on the screen too long. So I had to go out to the Pirate Bay while it's still afloat and get the movie. And here is a still of Matt pushing broom. And I understood the question. If you have any exposure to graph theory, the first two questions are trivial. All right, most people have zero exposure to graph theory, so I will give you some background. The problem was discussed endlessly by drunks in the Middle Ages in the town of Königsberg. That's a city in East Prussia, now called Kaliningrad, in Russia, now after the World War II land grab. The Pregel River runs through it. It's got 2 islands, 7 bridges, and 7 bars near these 7 bridges. They were all owned by the same family, and they had a standing bet. If you can walk over all 7 bridges one time and one time only, and end up at the starting bar, you get free beer for a year. Now you of course had to stop by each bar to mark your stamp, and while you were at the bar, you might as well have a pint. I mean, these were Germans after all. No one ever won the bet. But many got drunk. The 7 bars were the winners. And this became known as the 7 Bridges of Königsberg problem. Now, the biggest math nerd of all time, a Swiss named Leonard Euler, who spent actually a lot of his time in Germany and Russia, turned this into a math problem that is now called graph theory. You get these vertices and edges, and you take a vertex, multiply it by an edge, and you get back to a vertex. And the vertexes were for the land masses. There are two sides of the river and two islands, and 2 plus 2 equals 4, so there are 4 vertices total. And the edges are the bridges, the way to connect these things together, 7 in all. And what Euler noticed was that if there was an even number of edges connecting to each one of the vertices, then there's no trouble finding a solution. There's only an issue if there's an odd number of edges connecting to the vertices. If there are 0 or 2 vertices with an odd number of edges, that can work. The two odd ones kind of working together. However, if you've got a different number than 0 or 2, it doesn't work. And in the original problem, all 4 vertices had odd edges. So Euler proved that it cannot be solved. Now in the film, it is like the 7 bridges problem, with 2 of the bridges blown up by Allied bombers, as did happen in World War II. And if you get that bomber run just so, then all the vertices have an even number of edges going into them, so it's easy to walk each bridge one time. You can make a matrix out of the graph. That is what question 1 is about. There are 4 vertices, and there are 4 ways to connect them, so that makes 4 times 4, 16 numbers that we need to fill out. So this really is kind of like a Sudoku puzzle, which you probably aren't familiar with the rules, but they aren't so bad. The first is that there are no self-loops, so there will be nothing along the diagonal. And that takes care of 4, leaving only 12. Now the edges are all non-directional. You can go this way or that way, it doesn't care. And so the matrix must be symmetric. The numbers on the above the diagonal must reflect the numbers below the diagonal. So that leaves us with 12 divided by 2, 6. Now the triangle has one edge between 3 different points. 1, 2, 2, 4, and 4, 1. And so that takes care of 3. And then this 2, 3 connection, well that's actually a doublet, so we got to throw in 2's for that. And then 3 is kind of isolated. 3 doesn't connect to 1 or 4, therefore it's going to get 0s. And if we look at what Matt has written up on the mirror, he's spot on. Excellent work, Matt. Now, a person in math grad school had better be able to solve this problem, or they don't deserve to be in math grad school. Actually, an undergrad at MIT should be able to solve this problem. I mean, you just have to give them a hint. This is graph theory. That should be enough. Read up in Wikipedia, and you're a smart person. You should be able to figure it out. Now, the 3-step walk means that we're really just taking the cube of this matrix, and that also is trivial. The third question is about the generator functions for walks from I to j. Now that sounds scary, but it's kind of like once you get it to I, well, it's going to be how you get it to j, and the difference is going to be the difference between those two. And the fourth question is just take your generalized thing and deal with 1 to 3. I mean, it's just being a specific application of question 3. So despite all the great acting in the film, this math problem is both unimportant and easy. They did have a little continuity problem. The person who wrote up the problem the first time was not the same person who wrote it in the second time. Now, the math problem was the same, and the solution was right. And it may be it may be due to a Nobel Prize winner, because I noticed in the thank yous they had Sheldon Glashow who was a Nobel Prize winner, and he probably gave this problem to them and the solution because it had the loops. The graphs are kind of pretty. So he was probably asked for something that was pretty that he could fit on a blackboard, and he came up with this one. So I've got my own problem in graph theory, all right? And that is I've got a really sexy bit of math, graph theory, that I don't know how to sell. I mean, I don't think I can get Goodwill Hunting 2 funded, the story of an important graph theory issue. The most important stuff in mathematical physics are numbers. And that would be the real numbers, the complex numbers, and according to my own hypothesis, the quaternions and hypercomplex numbers. So I wanted to see the graph theory for all of these. And I could have done it, oh actually I did, with pen and paper, but it was so important I thought I needed to use clay and pipe cleaners, the favorite of young people. And this is actually probably the most important one of all. This is for real numbers. Because you start at this vertex here, 1, you multiply by 1, and you end up at 1. Why is this so important? Well, photons have been around for like 13 plus billion years. Electrons have been around for the same amount of time. How do they continue to exist from a mathematical perspective? An electron remains an electron. This is an automorphic map. In other words, they're going back to the same place that they started. They go forward in time, yet they stay the same. And so I think that's what that loop is all about. Now the next most important number are known as complex numbers, and they're used extensively in quantum mechanics. So let's get our graph theory for that. And here we go. Get a close-up, all right? Great. So, what's going on here? Well, we've still got the loop, good, of real numbers. It stayed there, okay? We now have this new vertex in blue. But now we've got these two different paths between these two. And that's because 1 times I gets you out to I, but to get back, you have to take I and multiply it by minus I. So these, so we've got two undirectional edges, those loops, made of real numbers, and we have two directional edges made up of imaginary numbers. And it's kind of neat that the real number helps this imaginary number stay in place. And I actually had to reshoot this whole thing because I'd forgotten this one. You know, it's like, but when I thought it through, that's the fun thing about doing mathematical physics is you can say, without this, this is like incomplete. It's wrong. It's not a complete story. But when you add it, it says, hey, you know, real numbers help imaginaries stay in place. And I really kind of like that. So let's go on to the quaternions. And here we got, an awful lot more lines. But it's basically kind of a continuation of, well, there's the real loop guy, and here's the I thing, and we've got a J up there, and we've got a K down here in Kelly green, of course. Each one of these has its own little vertex. And I actually made an animation of this because the scalar here has a different property. And that is that you can't point to it. And you can't point at time. And so that's why I thought it would be more appropriate to kind of imply that real thing is time. Because if this didn't persist in time, it would simply be nothing and then like blink into existence and then go away. But that's not really the way it works. So I think this is animating this graph is kind of closer to what it really does in a day in, day out kind of way. Now, there's yet another problem with this one if you actually go and make this, okay? And that is, it's really kind of tricky to get two pipe cleaners to go between two clay balls like this. It'd be much simpler if there was only one pipe cleaner between each vertex, and there it is. These are the oops, this guy fell out. These are the hyper-complex numbers, nice and simple, and I think these have to do with accounting for gravity, which would be really cool if that was the case. So the graph that was in the film, not very complicated. Now look at these two and think about them, particularly if they got animated. I bet we could cover a lot of turf with these two. And it's in fact my fundamental hypothesis that if there's any pattern of events in space-time caused by any sort of phenomenon, that this accounting system, this dual accounting system, would be enough to cover everything that happens. The quaternions will cover the Maxwell equations, the weak force, the strong force, and this will cover gravity kinds of stuff. But that's a really radical notion that nature is using kind of a double entry accounting. But the reason I think it gets away with it is because we're talking about multiplication here. See, there's only one way to add these four numbers together. Number 1 adds to number 1, number 2 to number 2, number 3 to number 3, to number 4 to number 4. But when you get to multiply numbers together, that's what allows this kind of complication to arise, and for nature to say, I'm going to use both in different contexts. I'm going to use this one for doing mass stuff, and I'm going to use this one for doing you know, EM and the weak force and all that kind of stuff. At least that is my hope. So, if we get back to the film and the problems raised in the film, I had never really, you know, calculated the cube of my adjacency matrix. I certainly was familiar with it, but I had never kind of played with it. And so just preparing for this very video, I went ahead and did that. And it fortunately was not a very complicated, you know, people go, how much space do you need? How much time do you need to solve a math problem? It all depends on the math problem. I mean, in this case, I just fired up Mathematica and said, what's the cube of this? What's this to the 4th power? Or what's this to the 5th power? I'm seeing a pattern, and I actually kind of wrote it on these sticky notes here. And I'll show it in the slide here. This is the generators for powers of, and it's very simple. It's always some power of 2 times something else. And it is a solution to a specific math problem that's a variation on what appeared in Good Will Hunting. Is it important? My guess is probably not. But that maybe nature does use it somewhere, and sometime somebody might glue this little bit into explaining some phenomenon that happens out there. I don't know. But that's what doing theoretical physics is like, is if you can get a question so specific and have your tools just refined enough, you can actually answer questions like this. And that's part of it that makes it a lot of fun. So I hope you learned something about the Good Will Hunting the movie and how it inspired some of my own work in theoretical physics. Thank you very much.
All the girls in the classroom think he's hot. He shows up wearing the sandals with the white socks. He hears them giggling while he's got his back to the class. He thinks he's got an eraser mark on his ass. And all the girls from the hall show up to hear him talk, even though most of the time he's covered in chalk. Math prof, rock star. Math prof, rock star. Oh yeah. Math prof, rock star. He And after hours outside of his office, there's a line waiting, full of girls who want to ask about their quadratic equations. She leans over the desk and twirls a pencil in her hair, complains the grade he gave her was way unfair. And all the professors, they laugh about it and they wish him well. The guys in the class are all just jealous as hell. Math prof, rock star.
I must confess that I lied to you, YouTube. My favorite part of Good Will Hunting was not all the math done at the blackboard. It was actually the scene at the Tasty, where they're talking about what they're going to do at their end of their date. And she's thinking about the goodnight kiss, and he's thinking about the goodnight lay. And then they do actually get the kiss, and it tastes like pickles. So I think that scene was just so much more realistic than one usually sees in a film from Hollywood. I confess to YouTube because I lied again. My favorite part of the film was not the part at the Tasty. It was this scene at 4:30 a.m. in her apartment where they're like totally naked, or actually partially naked, or something like that, and they're obviously having relations. And she says that she actually not going to have relations because he's not telling her enough. She wants to meet his friends, and so he says, well, I'll call up my friends right now, it's 4:30. They'll understand! That's believable, which is not too much like Hollywood. I must confess, YouTube, that I lied yet again. The favorite part of the film wasn't even in the film. It wasn't that scene at 4:30 in her apartment. It was the fact that Matt Damon and Minnie Driver were doing it off stage. Because I think when the actors and actresses do that, makes the scenes so much better. Think Bogey and Bacall. Brad Pitt and Angelina Jolie, Mr. and Mrs. Smith. Ben Affleck and Jennifer Lopez. Now the movie itself was really lousy, but the sex scene rocked.
Oh yeah.